Okay, welcome to another session of Introduction to Photonics. So, we had been talking about fundamental principles associated with a laser, and we are trying to quantify its characteristics both in terms of the output power, how it varies or how it increases as you increase the pump power. But we would also like to quantify the spectral characteristics. Okay. So, that is what we were at. So, we were actually starting from the basic conditions that you need to satisfy so that you have a laser built, and that essentially meant that on one side you are offsetting the loss in the cavity with the gain, and on the other side you are also saying that only specific frequencies can exist within the cavity, specific frequencies that corresponds to the constructive interference criteria of this Fabry-Perot cavity. Those are the ones that will survive. So, we talked about a case where you will have all these longitudinal modes corresponding to the case where the gain is greater than the loss. Those are the ones that will survive in the cavity, and specifically we went on to look at the issue which includes saturation of the gain. So, we said as we build up these photons inside the cavity through stimulated emission, you start reducing the gain also, to the point that when we were looking at what happens when you turn on a laser, I think we were talking about this particular picture. What happens when we turn on the laser is we have initially very few photons at the signal wavelength, and so you have a fairly high gain. That is what we call as the small signal gain, but as you build up more and more of these photons at the signal wavelength, the gain starts saturating. It may go to a point where the gain is actually saturated below the loss in the cavity, and at which point the gain recovers. Okay, and then it will go through some oscillations before it stops at steady state. And the key point that we noted was that at steady state the gain equals the loss. So, any more pump photons coming into the cavity is getting converted into signal photons, right. Any more pump photons that are coming into the cavity beyond the point where you reach threshold, beyond the point where the gain equals the loss, right, all those other photons will escape the cavity, and so we have a conversion of the signal photons or the pump photons into signal photons. So, in our last discussion we looked at the photon flux, right. So, this is the photon flux from the cavity and within the cavity, and that photon flux we essentially came up with an expression where we said it is phi sat multiplied by n naught over n threshold minus 1, where n naught corresponds to the small signal inversion and n threshold corresponds to the inversion required for achieving the lasing condition. So, any more inversion beyond the threshold inversion is going to result in the generation of these extra signal photons, which will essentially escape the cavity. So, that is what we are projecting over here, and we stopped at the point of saying, this conversion happens with a particular efficiency, and we wanted to quantify that efficiency, right. So, that is where we stopped. So, we said this could be look at phi s, or you could also look at it in terms of the output power as a function of the input pump power, and this output power, which will be given by h nu multiplied by the output signal flux. Okay. That output signal flux is actually only a fraction of the phi s, where phi s corresponds to the signal photons that are generated in the cavity. Okay. So, what determines that fraction? What determines that fraction that escape the cavity? The mirrors, basically the mirror reflectivity or the transmission of the mirrors. So, what we will find is, first of all, we will get an expression for that for phi out, and what we will find is that there is an optimum reflectivity, okay, for extracting this output power from the cavity. So, we will actually look at what is the optimum reflectivity, what is the expression for the optimum reflectivity. Okay. So, let us continue over here. So, what we are saying is this output power P out can be written as some efficiency, let us call that the slope efficiency, multiplied by the power that is available beyond threshold power. So, the cavity is going to consume a certain amount of pump power just to reach threshold. Any more power beyond that is getting converted to signal photons that are escaping the cavity, right. So, that is the output power that we are looking at. So, what we want to see is what is this quantity which we call as the slope efficiency, right, and that slope efficiency is just the slope of this output power versus input pump power, right. Now, we can actually say that the slope efficiency eta E. So, this slope efficiency can be expressed as, so if we have a cavity, let me just draw that cavity again. So, we have one mirror here, another mirror here. So, this is, let us say, reflectivity R1, this is reflectivity R2, and of course, we have the gain medium here, and we are tracking the output power in this direction. So, as far as the slope efficiency is concerned with respect to the power that we are monitoring coming out of reflector with the second reflector, we can say that corresponds to the fractional loss given by mirror 2 with respect to the overall loss, right. So, the overall loss is alpha r, where alpha r we said corresponds to alpha m1 plus alpha m2 plus the internal losses in the medium, right, inside the cavity. So, you can write the slope efficiency or is corresponding to the fractional loss for mirror 2 and divided by the overall loss. Now, overall loss we said is inversely proportional to what? We talked about the average photon lifetime inside the cavity. We said it is inversely proportional to the average photon lifetime, and we said alpha r is given by c, whereas c is the speed of light in vacuum multiplied by the photon, the average photon lifetime. Okay. And then what is alpha m2? Alpha m2 corresponds to the mirror loss, which is given by 1 over 2L ln of 1 over R2, right. Where did we get that 1 over 2L? That's just the 2L corresponds to the round trip propagation, but we are normalizing the mirror loss with respect to 2L, so that all of this overall resonator loss can be represented as a per meter basis, right. Alpha int is distributed across the medium, whereas the mirror losses are just lumped elements at the ends. But when we are looking at alpha r, it is a per meter quantity. So, just so that we have everything equivalent, we are basically taking a lumped quantity and making it like as if it is distributed across the cavity. But physically that the mirror losses are just a lumped quantity, it is not a distributed quantity, okay, right. So, I can put all of this together and get an expression for the slope efficiency, which is going to be C over C multiplied by tau photon, that is a photon lifetime, divided by 2L ln of 1 over R2. Okay. So, does this make sense? What are we saying here? Maybe it will make sense if I represent it slightly differently. 2L over C, what does that correspond to? That corresponds to some time, right. So, what is that? That corresponds to the round trip time for a photon inside the cavity, right. So, I can write this as tau photon over tau RT, where tau RT corresponds to the round trip time inside the cavity, right. And ln of 1 over R2, if R2 is my reflectivity, let me say that T or maybe T2 corresponds to the transmission of this mirror. So, I can basically say that R2 plus T2 has to be equal to 1 for energy conservation, and so R2 can be represented as 1 minus T2, right. And if T2, which corresponds to 1 minus R2, is far less than 1, if it is very low transmission, then I can basically say that ln of 1 over R2 is approximately equal to T2, right. So, ln of 1 over a very small number can be approximated as that number itself, right. And so, I can write this as T2, okay. This I should say is approximately, this is valid only when we have a very low transmission, right. So, what does that tell you? I am just writing it so that we can get a little bit of insight into this. So, if we want high slope efficiency, if we want high conversion efficiency for the pump to signal photons beyond the threshold, right. So, you lose certain energy to overcome the losses, right, that is your threshold pump power. So, forget about that, but beyond that threshold, if you want to convert that pump photon to signal photon with higher efficiency, I need to have a long photon lifetime. Long photon lifetime will allow me to keep multiplying the signal photons within the cavity, right. But that by itself does not help, okay. You also need to extract this power from the cavity. So, you need to have a transmission, you need to have sufficiently high transmission so that you can extract power from the cavity, right. So, these are contradicting requirements. To have long photon lifetime, what do? You make a very low loss cavity, which means that you need very high reflecting mirrors, but it does not help that you have so high reflecting mirrors that all the power remains within the cavity. You need to extract some power from the cavity, right. So, you need to leak out a little bit, but then the question is, how much do you leak out? Is there an optimum value for T2, right, where you leak out without compromising the buildup of power within the cavity, right. So, you need enough signal photons to keep that stimulated emission going. You cannot compromise that. If you go for very high extraction, very high value of transmission for this mirror 2, then you have very high loss. If you have very high loss, not only is your threshold going to be higher, but the buildup is also not very good, right. So, do you understand the contradiction? On one hand, you can actually get to very low thresholds, right, or in this case you can also say it can give very high slope efficiency by making highly reflecting mirrors for both R1 and R2 are basically high values, but in that case you are not extracting much power from the cavity, and but on the other hand, if you try to extract a lot of power from the cavity and by making one of the mirrors low reflecting, which corresponds to high transmission, right. In that case, you may not have enough photons to sustain the laser oscillations, so sustain stimulated emission. So, we need to, there is an optimum value for T2 which you need to figure out, right. So, let us try to figure that out. Any questions up to this point? So, let us say, so on a optimization of output coupling, right. So, let us assume R1 equal to R2. Of course, we can change that assumption also. I will just come back to that in a minute. But if you assume R1 equal to R2, then what you are getting, the photon flux that you are getting out is corresponding to the photon flux that you have built in the cavity divided by 2 multiplied by T, let us say T2 in this case, right. If you are extracting, if you are looking at the light out of mirror 2, I said divide by 2 because there is a similar extraction happening from mirror 1 also, right. In fact, I do not want that. What is the point of having a laser like this and light going this way, light going this way, right. You are going to utilize the laser to do something in one particular direction. So, you do not want light going from here. So, what do? You make R1 as close to 1 as possible, okay, so that everything escapes out of R2. And if you have that condition, that factor of 2 will go away, because you are extracting everything out of one end, okay. You understand that? So, I am just being consistent with what is giving in Saleh and Teish, the textbook. Now, phi s, I have an expression for phi s. Is it here? Maybe here. So, phi s I have expressed in terms of phi sat and then the small signal gain and the total losses, okay. So, I can use that expression over here. So, I can write this as phi sat multiplied by T2 divided by 2 gamma naught, which is the small signal gain, divided by alpha r minus 1, right. So, I can just substitute, instead of phi s, I can substitute phi sat and this other part. Now, what do we want to optimize? We want to optimize T2, but T2, if you look closely, is not just sitting in the numerator, it is sitting in the denominator also. Where is it sitting in the denominator? As part of alpha r, right. So, alpha r, which I say is alpha int plus alpha m1 plus alpha m2, right. I can, I want to isolate alpha m2, right, because that is what I want to optimize. So, I can just basically say this is alpha int plus alpha m1 is alpha L and alpha m2 is 1 over 2 L ln of 1 over R2, right. And 1 over R2 I can write as, R2 I can write as 1 minus T2. So, I can just write this as this equals alpha L minus 1 over 2 L ln of 1 minus T2. Why do I get a minus sign over here? Because it is 1 over 1 minus T2, I have just taken as ln of 1 minus T2, in which case there is a minus sign that comes outside, okay. And this I can further write, I can take 1 over 2L outside, okay, as a common factor, and then what I have is some total loss, let me call that Lx, right, that is extra loss minus ln of 1 minus T2, where Lx corresponds to 2L multiplied by alpha L, where alpha L corresponds to alpha int plus alpha m1. Okay. Why I am doing all of that will be obvious in a minute, so just bear with me. So, I am just going to substitute that expression for alpha r over here. So, I will have phi sat T2 over 2, and here I am going to have gamma naught multiplied by 2L divided by this loss factor Lx minus ln of 1 minus T2 minus 1. Okay. So, here lies the contradiction. So, you can say that when T2 is very small, right, then ln of 1 minus T2 can be written as plus T2. So, that will be Lx plus T2 sort of thing in the denominator, and T2 is very small, that is the assumption that we started with. If T2 is very small, then that factor essentially is very small with respect to the extra loss factor. So, T2 has very little effect in the denominator. For small values of T2, it is dominated by what is in the numerator. Okay. But for larger values of T2, you start having the denominator come into the picture. So, then it will essentially start playing a role in terms of the power extraction. So, if I were to plot this function in general, right, let me just say the output flux, normalize it with respect to the saturation flux, because the saturation flux we know is a constant for a given gain medium. What does the saturation flux depend on? That is the excited state lifetime as well as the emission cross section. Okay. So, that will be a constant for a given medium. So, I can just take that out of the equation. That is not a variable that I am interested in. What I am interested in the x axis is T2. Okay. So, if I plot this, I will get some function like this. Right. At small values of T2, the whatever is in the denominator is negligible, right. T2 does not have that part you can neglect, and so it's proportional to T2, right. The output flux is proportional to T2, and then so then as you increase T2, you will have increase in the output flux and also the output power. But as you increase T2 further, you start having the denominator come into the picture. So, then that will end up reducing phi out. Okay. So, we are looking at what is this optimum value? What can you say about this point? That is a point of inflection. What happens at the point of inflection? The slope is 0. So, the derivative of phi out with respect to dt2, that is 0 at that point, right. So, what I can do is apply that I can take a derivative of this entire expression corresponding to phi out with respect to T2, and also under specific conditions. So, if I am looking at d phi out over dt2 equal to 0, and when T2 is far less than 1, such that ln of 1 minus T2 is approximately equal to minus T2, right. If I have those two incorporated, then I will come up with a final expression which says that the optimum transmission is going to be given by G naught into Lx to the power of half minus Lx. Lx corresponds to the extra loss. So, this is what you get as the optimum transmission for this cavity. This cavity where I should also mention where G naught corresponds to gamma naught multiplied by 2L, right. That is the gain factor. This is the gain factor for our cavity, and Lx corresponds to the extra loss factor inside the cavity. Okay. If you look at specific values, these values are used by your book. If we say G naught is 0.5 and Lx corresponds to 2%, which is 0.02, then in that case what we find is this is about 0.1, 0.2, 0.3 and so on. That is 10%, 20%, 30% transmission, and this is 0.1, 0.2 is way up there and so on, right. So, we find that for these values you find that the optimum transmission is roughly about 8%, right. So, and if you have higher, so what this tells you is if you have higher gain, right, if you have higher gain inside your cavity, while you freeze all other losses, then you can afford to push this optimum point to higher values. Then you can afford to use higher transmission, extract more power from the cavity. Okay. So, that is the physical feel for that. So, let me stop at this point.